Physical science time. Okay, go sit down. Today we have two things to talk about. We're talking, let's finish our talk about ionic bonding really fairly briefly, although this will be the more complicated part. Let's call this, we called the last one, I forget which order I put it in. Did I call it naming compounds and writing formulas, or did I call it naming compounds and writing formulas?
Formulas and naming compounds.
Writing formulae. You can put formulas if you want.
Sorry.
And naming. Shh. Please be quiet. I know it's Friday. Please be quiet. I'm not trying to throw shade on my homies, but this might be the only class that is currently learning today or may do learning at all today, so please learn. Writing formulae and naming compounds. Part 2. Part 2, because we're doing part 2 now. We're still talking about ionic. We had a flow chart yesterday that it kind of broke apart as we were going along. But we had a flow chart yesterday which was, first, how do we figure out if a substance is covalent or ionic? And that was, if it's covalent, it'll have only nonmetals, and if it's ionic, it'll have metals and nonmetals. And then we had if it's binary or complex. Binary, only 2 elements, complex, more than 2 elements. And now we have the next part of your flow chart, so hopefully you still have your flow chart from yesterday. The next part of your flow chart is, so we had ionic or covalent, probably not in that order. And then within ionic we had binary, complex, and now we have transition metals. What's a transition metal and where do they live?
Transition metals down here.
Yeah, the transition metals are all the ones in this little bottom part of it. Like if we pretend the periodic table, this is not what she looks like, but if we pretend, especially that part, but if we pretend this whole thing is the boat, see that? Nice, this is a good drawing. The little bottom part of the boat, the midships, as we would say in the Navy, isn't that right? The bottom part of the boat here is the transition metals. So if something is from this part of the periodic table, we have a separate special set of rules. Okay? So far, so good. Let me repeat that for those of you who are, instead of listening, playing with your hair. Let me repeat that. If we have something from this part of the periodic table called the transition metals, we have a separate special set of rules, okay? We do like these rules. We love these rules. You're not going to be good at them, but you will. We're only going to kind of cursorily learn it right now. That means like we're only going to go over it a little bit, and then next year, no, probably the year after, when you're in chemistry, we will talk about it quite a lot. So the point of this is, since transition metals can have multiple, what we call oxidation states. Remember oxidation state, at this level, oxidation state, this is one of your vocab words if you remember. Oxidation state is the same as, these are not identical, but at this level we'll say they're the same. Oxidation state is the same as the charge. So what's the oxidation state of chlorine? When it bonds, oxidation state of chlorine when it bonds is? No. It has 7 valence electrons, but that means its oxidation state, its charge when it bonds is?
1.
Who said -1? Raise your hand. -1 is correct. So the oxidation state of chlorine is -1. It gains a -1 charge when it bonds. That's what the oxidation state is. Since the transition metals, this is very important, please write this down. Since the transition metals can have multiple oxidation states, since transition metals can have multiple oxidation, I wish my phone wasn't ringing, you're just going to have to ignore it, oxidation states, that's plural. Since transition metals can have multiple oxidation states, we must include the, I'm going to abbreviate oxidation state as OX state, in the, fill in the blank, what do you think? Where are we going to have to include the oxidation state?
In the transition period.
Well, what we're doing is we're naming and writing formulas. In the name, actually.
I really want that.
Since transition metals can have multiple oxidation states, we must include the oxidation state in the name. All you have to do is first, Taylor, be a really melancholy person. Like just go about your life going, blah, 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 That's like I do, and then that leads you to have oxidation states. Ringtones, like that, yeah.
What if your son is choking on a piece of carrot?
Please don't joke about that. Okay, since transition metals can have multiple oxidation states, we must include the oxidation state in the name. So, look at this one. Give me an example. Here is, hey, what's this guy? Boy, you guys are really freshmen. Thank you, Fate. Fate is also a freshman, but he is a blacksmith and metallurgist, so he knows that this is copper. So copper, sulfide. Good. Hey, that's pretty good. It's wrong, because what we have to do is we have to include the oxidation state in the name. Let me tell you, because there are two kinds of copper. Oops, sorry, that's wrong. There are two kinds. These both exist. This copper sulfide exists, and this copper sulfide exists. These are both copper sulfide. These are both copper sulfide, but they have totally different properties. This one, black. This one, I don't actually know, but it's probably different. They have totally different properties. So how do we tell in their name which one is which? We have to include the oxidation state, and this is how we do it. Copper, what's the charge on this one? This is where we have to kind of work backwards. What's the charge on the sulfur always? Look at where she is on the periodic table. It has 6 valence electrons, so what's her charge?
-2.
-2. So what must this sulfur be also? -2, because sulfur is -2. So if this one's -2, and it's bonded 1-to-1, how do I know it's 1-to-1? Because there are no subscripts. With this copper, what must the charge on the copper be? Remember, we have to add up to 0, so it must be +2. Do you see we had to work backwards to find that? Uh-oh. Look! This is -2, but there are 3 sulfurs, so it must have a total charge of -6. So what must the charge on each copper be in this case? No. +3. Look, they're different. The only thing that's different about these is the charge of the copper, the oxidation state of the copper. So what we write is, what's the oxidation state of this guy? Oh man, you should really, hey, let's all say it. What's the oxidation state of this guy? +2. So what we write is, please write this down, copper 2, that's in Roman numerals, and it's in parentheses. Sulfide. For this one, we would write then instead, for the other one, we write copper 3 sulfide. So then you tell me, and I'm going to yell this at you 100 times, even probably during the test, what does this Roman numeral stand for? Okay, I'm not asking what number it represents. I mean, what property of the copper is this? Is it how many there are? It's the oxidation state. Thank you, Faith. Let's really write that down in giant print. This, great. I used the dead marker too. Let's write this down in giant print on the top of our page. This, in Roman numerals, is the oxidation state. It is not how many there are. That's wrong. People are always trying to do that, but that's wrong. It's not how many there are. It is the oxidation state. We'll talk more about this as we do more practice problems on your worksheet, and I will help you with this on the test because, like I say, this is a cursory introduction to it, so you're familiar with it, but I don't expect you to be pros at this. Thank you. I don't expect you to be pros at this right now. We will do this more when you're in chemistry. I want you to be introduced to this now. I want you to have it in your notes. But when it comes time for the worksheet, we're going to do that together. And when it comes time for the test, I will help you with these on the test. Is that understood?
Yes.
Okay. Hunter. No, I wouldn't if I were you, but it's up to you. Okay. I'm going to move the covalent over here like it was yesterday. The covalent, we're going to talk about covalent bonding now. This one usually, remember I told you about the bell work, that people usually find naming the ionic compounds easier than they do writing the formulas. And that's fine. It's just a less complicated process. But usually people find covalent naming to be the easiest of all. So let's go through that process right now. I'm not saying that that has to be you, and if you don't feel guilty. But covalent naming usually people find to be the easiest of all. The trick about covalent naming is that you have to know which things are covalently bonded. Do you remember how to tell? Like if you're just given a substance, how do I know if it's covalent or ionic? Because we have different rules.
Please excuse the interruption. The following students still need to pay for their prom meal. $20. Ketlin, Hayden Mareva, and Tiana. These will be paid today by the end of the day. Thank you.
Let me say that sentence again, and you can focus back up. Please stop talking. In order to figure out if we have covalent or ionic bonding, because they have different rules, so we need to know that, covalent is only nonmetals, and ionic is a metal and a nonmetal. Here are the rules for covalent naming. We have a series of Greek prefixes we give them based on how many there are. They are these, and you need to write these down. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, and there are more, but these are the ones we need to know. These each represent a number. What's mono probably represent? 1. What's di probably represent? 2. Tri? 3. Tetra? 4. Penta? 5, 6, 7, 8, 9, 10. Mono, you should know, means 1.
That means when
Like a, no, that's mononucleosis, which is the name of that organism that only has one nucleus, which is pretty usual. Anyway, but mono, like if you ever pay attention to the settings on your television, mono in the audio setting means it's only going to come out of one speaker. Mono means 1. Di means 2, as in the diatomic molecules all each had 2 atoms of one element. Tri, as in tricycle, has 3. Tetra, kind of like a tetrapod. We talked about those in 8th grade. Remember that was a creature with 4 limbs. Also Tetris, all the Tetris blocks have 4 little baby blocks in them. Pentagon, hexagon, heptagon, octagon. The rest of these are just the names of the polygons that you probably already know, those prefixes. Yes?
This might be a really stupid question.
No?
But, like October, November, December.
Yeah, it really does. That's a great, if we had a little bit more time, I'd talk more about that. But basically, these used to be the 8th month, 9th month, and 10th month of the year. And then, well, they were always 12, but then some Caesar said, you know what, I want these other months named after me, and so they just shoved them in, and the months all bumped back to. Anyway, so we have these prefixes that we add. So, and it's really pretty easy. If we have, for instance, C2S, we call it dicarbon sulfide. We still name them in the order they're given. We just put whatever the number of it is, we put that prefix before it. Let's do this one. CO2, you already know what that is. What's the C? Carbon. What's the, if there's 2 O's, then it's dioxide. P4S5. What about that one? Well, what's the P? You have a periodic table, and there's also one in the room. What's the P? Phosphorus. If there are 4 of them, instead of just phosphorus, it's now tetra, tetraphosphorus, tetraphosphorus. And if there are 5 sulfurs, it's not just sulfide. We still change the "ide" at the end. It's not just sulfide, it's now pentasulfide. That's it. That's the whole rules for covalent, is however many there are, we shove that in Greek onto the front of the name. And then it's even easier to go from name to formula because you just say, oh, there are 4 phosphoruses and 5 sulfur. Only kind of unconformity about it is that sometimes we don't include the mono. In fact, we usually don't include the mono. Mono is only usually included if we're trying to differentiate between something that's generally more than 1 but now has 1. For instance, in carbon dioxide, if we're instead talking about carbon monoxide, that means there's only 1 oxygen. We usually use it just to identify when there's something less than what we would expect. So, the name is just the name of the things with the number stuck to the front in Greek. And then the formula, you just write the things with how many there are based on the formula or on the Greek names. Okay, do you have, let's do, actually, I don't have your worksheet anymore, but let's do a couple of practice ones since we have a couple minutes here. Oh, before we do that, do get out your worksheets. Before we do that, does anyone have questions about this thing about the transition metals? Remember, as long as you kind of understand this at a surface level, you're okay with this for the transition metals, ionic naming. Does anyone have questions about the covalent naming, or either of them? Okay, I'm sure you will. Not yet. I'm sure you will. I'm sure you will as we do the worksheets, but remember, we're going to spend class on Monday doing worksheets together. Okay, but we're not done yet, so. Okay, let me see. Hey, what are you doing? I did not say pack up your stuff and go away. I said get out your worksheet. We're not done. We're working on some practice problems. Yeah, go sit down so we can work on some practice problems, please. Yes, that's the one. I want to thank you, Shylin. I appreciate you sharing with me. Hey, conveniently, on your worksheet, these are just, I think, at least this page, it just tells you whether they're ionic or covalent. That may or may not be true on the test. You need to be able to identify whether they're ionic or covalent. But on the ones that just say covalent, let's look at 19. This is going to be our little practice box up here. Let's look at 19. Get out of there. 19 says NO2. Okay? Someone tell me what's the name of the first guy? Nitrogen.
Oxygen.
And then the second one, do I just write nitrogen, oxygen?
No, you write nitrogen dioxide.
Hey, it's not, remember, it's not dioxygen. We still change the ending of the second one to "ide," so now it's dioxide. Good. Okay, let's do 24. B2SI. What's B?
Bromine.
Nope. What's B? Boron. But there are two of them, so it's not just boron, it's
Diboron.
diboron. And then what's Si? Silicon. Silicon. Silicone is a kind of plastic. Silicon is the element. But silicon, we need to change the ending to "ide," so it can't just be silicon. It needs to be silicide. Diboron silicide is 24. Let's look at 27. Oops, let's look at 29. And 29 says hydrogen iodide. Uh-oh, this one doesn't have any prefixes. Well, how many are there then?
One.
There's just one each, so it's just HI. Let me ask you this question. Do you find the covalent ones to be easier than the ionic ones were? Okay. That's usually the case. Diboron. That means that there are two. Remember, we used this little chart. Does everyone have this chart written down?
Yeah.
I think this is given to you on the test, but do have it written down in your notes just in case you can use your notes on the test. Any questions? You do still have about, well, you have 24 seconds, so we probably won't have time to work on this.